Welcome to G Fun Facts Online. Today we are going to dismantle the biggest metaphor in modern history, the cloud. We talk about the internet as if it is ethereal, a weightless magic that floats above us, accessible through panes of glass. But the reality is heavy, loud, and intensely physical. It is built of steel, concrete, fiber optic glass, and copper. It consumes rivers of water and enough electricity to power nations. This is the story of the hyperscale data center, the factory floor of the 21st century, and how in 2025, it is undergoing a radical transformation driven by the insatiable hunger of generative AI. To understand the physical internet, you first have to grasp the sheer scale of the infrastructure we have built. As of early 2025, there are over 136 hyperscale data centers in operation globally. That number has doubled in just 5 years. But the raw count is misleading because the size of each individual facility is exploding. A decade ago, if you built a 10-megawatt data center, you were a titan of industry. Today, that is a rounding error. Hyperscale campuses operated by the Big Three, Amazon Web Services, Microsoft Azure, and Google Cloud, along with Meta, routinely exceed 100 megawatts. We are even seeing gigawatt-scale campuses in the planning stages. That is not a computer room, that is a small city. When you approach one of these modern hyperscale campuses, it does not look like a tech headquarters. It looks like a high-security logistics terminal or a fortress. The buildings themselves, often called the shell, are windowless monoliths painted in neutral grays or whites to reflect heat. They are engineered to survive natural disasters, from tornadoes to earthquakes, but the security starts hundreds of feet away at the berm. This is a layer of landscaping designed as hostile vehicle mitigation. It looks like a nice grassy hill, but it is engineered to stop a truck bomb without looking like a military checkpoint. Perhaps the most critical component of the exterior is the power substation. A hyperscale campus often has its own dedicated substation, pulling high-voltage power directly from the transmission grid, completely bypassing the local distribution lines that power your home. This is necessary to ensure stability because these buildings are voracious energy consumers. And cloud architects are paranoid. They do not trust single buildings. They build in what are called availability zones, or AZs. An AZ consists of one or more discrete data centers with redundant power and networking. A region like the famous AWS US East one in Northern Virginia is a cluster of these AZs. They are positioned carefully, close enough, usually within 100 kilometers, to replicate data synchronously with low latency, but far enough apart that a flood, tornado, or even a nuclear event hitting one AZ is unlikely to take out the others. Now, let's move inside. Until about 2023, data center design was evolutionary, slow, steady improvements. In 2025, it has become revolutionary. The culprit is generative AI. Traditional cloud workloads, like your email or a database query, are what we call bursty. They spike and drop. But AI training workloads are different. They are massive, continuous mathematical crunches that run for weeks or months at 100% utilization. This has forced a complete redesign of the facility's interior, centered around the problem of density. For years, the industry standard for power density was roughly 6 to 8 kilowatts per rack. That is manageable. But in 2025, an AI training cluster utilizing high-end GPUs like the NVIDIA Blackwell pushes that rack density to 80 kilowatts, 100 kilowatts, or even 120 kilowatts per single rack. To put that in perspective, if you placed these 100 kilowatt racks in a traditional data center layout, they would literally melt the floor tiles and overwhelm the air conditioning instantly. AI data halls are now designed with lower rack counts but vastly higher power cabling and reinforced weight-bearing floors just to support the heavy copper and the new liquid cooling systems required to keep the silicon from frying. This brings us to the most significant shift in data center physics, the death of air cooling. For 30 years, we cooled computers by blowing cold air on them. We had giant chillers on the roof cooling water, which ran through handlers to blow cold air through a raised floor. But in the AI era, air is dead. Air is simply not a good enough conductor of heat to cool a chip running at 350 degrees Fahrenheit. If you walk into a cutting-edge AI data hall today, it sounds different. The deafening whine of thousands of server fans is gone, replaced by the rhythmic hum of pumps. We are seeing two main technologies here. The standard for hyperscalers right now is direct-to-chip cooling. This involves a cold plate sitting directly on top of the GPU and CPU. A liquid coolant, often a glycol water mix, circulates through the plate, absorbing heat right at the source. This captures about 70 to 80% of the heat. But the frontier, the stuff that looks like science fiction, is immersion cooling. This is where servers are vertically dipped into tanks filled with a mineral oil-like dielectric fluid. The liquid touches every component. In two-phase immersion, the fluid boils off at hot spots and condenses on a coil at the top of the tank. It looks like a boiling cauldron of electronics, but it is the most efficient way to cool high-density silicon. Of course, all this cooling and processing requires energy, and that is the single biggest constraint on the physical internet today: electricity. A single large AI query uses as much electricity as fully charging a smartphone. Training a model like GPT-5 requires gigawatt-hours of energy. The electrical grids in places like Northern Virginia's Data Center Alley, Dublin, and Singapore are buckling under the load. To solve this, big tech has made a move that would have been unthinkable a decade ago. They are going nuclear. The tech giants are effectively becoming utility providers. In late 2024, Microsoft signed a historic deal to restart Unit 1 at 3 Mile Island. Yes, the site of the 1979 accident. It is being resurrected solely to feed the Azure cloud with carbon-free baseload power. Meanwhile, Google and Amazon are taking a different approach, investing in small modular reactors, or SMRs. Unlike traditional massive reactors, these are factory-built, salt-cooled reactors that can be deployed faster and more safely. By 2030, the plan is to have behind-the-meter nuclear plants, reactors, sitting right next to the data center, disconnected from the public grid entirely, providing dedicated, clean power 24/7. If power is the blood of the data center, fiber optics are the nervous system. The physical internet is a mesh of glass strands thinner than a human hair, pulsating with laser light. And contrary to popular belief, satellites handle almost none of this. 99% of international data traffic travels underwater. The ocean floor is crisscrossed with cables roughly the thickness of a garden hose. Historically, telecom carriers like AT&T or Verizon owned these cables. Today, the hyperscalers own them. Google, Meta, Microsoft, and Amazon have become the dominant investors in subsea infrastructure. The map of these cables is changing too. We are seeing a massive surge in trans-Pacific cables connecting the US West Coast to Japan and Southeast Asia, specifically bypassing geopolitical choke points like the South China Sea. There is also the new Humboldt cable connecting South America directly to Australia, creating a completely new Southern Hemisphere route. All these cables eventually surface and terminate in what is arguably the most valuable real estate in the world, the Meet Me Room. Located inside carrier-neutral data centers, the Meet Me Room is where the networks physically touch. Imagine a room filled with yellow fiber cables from AT&T plugging into a patch panel, connecting to blue cables from Netflix, which connect to red cables from Google. This physical cross-connect is where the internet actually happens. It is the handshake between networks. Now, let's look inside the actual racks. In the past, companies bought servers from Dell or HP. But hyperscalers realized that off-the-shelf gear was full of waste, unnecessary plastic, video connectors, and bloated casing. So they started the Open Compute Project, or OCP. If you walk down an aisle in a Meta or Google facility, the servers look raw. They are vanity-free. There are no logos, no bezels, no VGA ports, and no unnecessary LEDs. They have even changed the size of the rack. The standard 19-inch rack has been replaced by the OCP 21-inch rack, allowing 3 motherboards to sit side by side to maximize density. They have also stripped out the power supplies. Instead of every server having its own inefficient power supply unit, a centralized power shelf converts AC to DC for the whole rack. This saves millions of dollars in electricity across a campus, and the silicon running on these boards is increasingly custom. AWS runs on their own Graviton CPUs and Trainium AI chips. Google uses Axion and TPUs. Microsoft has Maya and Cobalt. By designing their own chips, these companies strip out logic they don't need, optimizing strictly for the workloads they run. Security in these facilities is designed in concentric circles, modeled after onion layers. It starts at the perimeter with 24/7 armed guards and crash-rated fences. But the most intense part is entering the building. You have to pass through a man-trap. This is a small glass booth where you badge in, and often you are weighed. This weight check ensures you aren't carrying unauthorized hardware in or out. You pass biometric scanners, iris or palm vein readers, before the second door opens. Once inside, only technicians with specific tickets are allowed on the server floor. And what happens when a hard drive fails? It never leaves the building. It is shredded on-site into confetti. Google and AWS use industrial shredders that reduce storage media to dust to ensure not a single kilobyte of customer data can ever be recovered. Finally, we have to talk about the sustainability paradox. The data center industry is the largest corporate purchaser of renewable energy in the world, yet its environmental footprint is growing. Cooling requires billions of gallons of water. In drought-stricken areas, data centers are actually competing with farmers and cities for water rights. To combat this, companies are setting water-positive goals, investing in wetland restoration, and using adiabatic cooling, which uses outside air for cooling whenever possible, only misting water on the hottest days. On the carbon front, while companies claim 100% renewable energy, they often achieve this by buying renewable energy certificates to offset brown power taken from the grid. The new standard, led by Google, is 24/7 carbon-free energy. This aims to match energy consumption with clean generation hour by hour, not just annually. This is exactly why those nuclear deals are so critical. Wind and solar are not always available when the servers are crunching data at 3 a.m. So where do we go from here? The future holds some wild possibilities. We are seeing the rise of edge data centers, fridge-sized cabinets sitting at the base of cell towers to process self-driving car data in milliseconds. We have startups testing orbital data centers, putting servers in space to use the freezing vacuum for cooling and solar arrays for power. And Microsoft's Project Natick proved that we can sink data centers to the ocean floor. Sealed in nitrogen-filled pressure vessels, they cool naturally, and the absence of oxygen prevents corrosion, making the hardware last longer. By 2030, we might see lights-out automation, where the data center has no humans inside at all. Robots will swap failed drives and move racks, allowing the facility to operate in total darkness, perhaps even with lower oxygen levels to prevent fire. The physical internet is a testament to human engineering, a global machine made of millions of spinning disks, optical lasers, and silicon brains. As we lean harder into the AI era, these cathedrals of computation will consume more of our resources, land, and energy. The cloud is not magic. It is concrete, copper, and nuclear power. Thanks for listening to G Fun Facts Online.